So this time looking at a halohydrin reaction, a reaction with an alkene in the presence of a halogen like bromine, and in aqueous conditions with a plentiful supply of water. Because the alkene in that double bond is electron enriched, it's acting as a nucleophile, while the halogen is initially acting as the electrophile, and that's because of the capacity for that chemical bond to spontaneously polarize as it gets close to the electron-enriched source. The electrons can polarize towards the far side bromine atom, making the near side bromine atom feel electron deficient. So the nucleophile alkene uses those pi electrons to form a new bond to the bromine atom. The existing bromine to bromine bond has to break, sending the electrons back to the far side bromine, and we produce this carbocation intermediate. Positive charge on one carbon and the bromine attached to the other. There's also some bromide ions kicking around, which make for a good nucleophile, but the bromine, which is already on the carbocation, is closer and can respond quicker and use a pair of its electrons to make a new chemical bond. So we plug in that gap, that electron deficiency, and we make that bromine to carbon bond, and we'll produce as a resonance structure this bromonium ion bridge of our intermediate. Positive charge now on the bromine, and the two resonance structures together explain the geometry of the next step. We're looking at an anti-addition geometry. The first structure shows us the electrophilic nature of the carbon atom here, which is why the water is going to attack this atom. The second molecule, the second resonance structure, with that big fat bromine atom on top of the cycle, explains why the molecule of water has to attack from underneath. So the two resonance structures together explain the chemistry coming up. The ion bridge has to be avoided, and so the water, as a better nucleophile, comes in from underneath, making a new bond to the carbon. The existing bond to the bromine has to break, and will produce this halohydrin molecule, which is almost finished. We've just got that positive charge on the oxygen to take care of, and in this last step the molecule of water acts, this time instead of a nucleophile, attacks as a base, picking off that proton, and the electrons go back to the oxygen, and so we get a tidied up final product, the halohydrin, which follows the anti-addition, and the stereochemistry is specific because the two groups are attached on the opposite sides of the ring, so we also say that the reaction is stereo specific.